Okay, everybody, let me say hi. My name is Phil Hopkins, and I'm instructor with Linux Foundation right now. I'm recently retired from Rackspace. I'm one of the old guys around here in the industry. I've been around for, well, we won't say back when. It's been a while I've been working in this thing, and have done a number of different training sessions. I've trained everything from onto Red Hat and on Linux Foundation products. I have done OpenStack products, and so I've been doing this for a while, and we'll talk about today. We're going to give an introduction to some basic things of what have enabled all this cloud stuff we see and all the cloud technologies. Because without virtualization, without containers, we really wouldn't have a cloud. And so that's what we're going to spend our time looking at today. You can also see my innovative Twitter handle. That's not my Twitter handle, sorry. I have a Twitter handle. I forget what it is. I set a Twitter account up about 2009, 2010, and have not logged into that account since then. Whether it still exists or not, I don't know. But I'm not a big Twitter person. So just if you do need to get a hold of me, my email account is really easy. It's phil.hopkins@gmail.com. You can see how long I've been in Gmail. I was one of the early users, so I got my name. I don't have any numbers, any fancy thing there. So if you want to contact me, please email me. That's the best way of getting a hold of me. So let's go ahead and talk a little bit about virtualization. There's a few familiar faces in here, and a bunch of new folks that I haven't met, and I hope that this will be worthwhile to you. Let's click over on that. There. So what is virtualization? Why do we do it? What do we care about? Where did it come from? And I'm not going to get too much in the history of it, but I will mention a couple things about virtualization and its history. Virtualization actually goes back way back into the 1970s even. IBM started doing virtualization on its mainframes because the mainframes they came up, they found out very quickly that they had much more compute resource than the applications could use. And so the way is, how do you divide that up into some more applications can run and do things at the same time and allocate pieces of that resource, which they started innovating in and creating back in the 1970s. We come up to 2018, we've made a number of strides in how we do that and a number of different technologies, and we see new technologies springing up almost every year or every couple of years of how to fractionalize that and use it in different innovative ways. And we're going to talk about and look at how some of these pieces have come about and how we use them and how they make sense to you in some of the application situations. So let's jump into that, and kind of just so you know, I used to be a principal engineer at Rackspace. I have had almost every Red Hat certification known to man. I work and help the Linux Foundation. I've helped write a couple of the, maybe I shouldn't sell this, but the first Linux engineer exam I helped write the questions for and have done that. So I've been around and done a number of things for the Linux Foundation for various things. And I have some experience in this. I used to teach a number of classes in networking and OpenStack, and I have a heavy background not only in virtualization, but also in networking. So I do understand both those pieces. So we're going to take today, what is a hypervisor? What is virtualization? What's this all about? Why do we care? As the description says, why are there so many of them? Why do we have different kinds of hypervisors? What is a container? Why do we do that? Why do we care? And what are the bits and pieces? And you've probably heard of something in containers called Kubernetes. We're going to hit into what that is also. That's the latest hotness, and I'll give you kind of some opinions on that. We'll also hear all this alphabet soup of as a service. I call it the asterisk as a service or X as a service. We're going to talk a little bit about what those pieces, why do we care, and also OPNFV, not OpenNFV, but OPNFV and Cloud Foundry is a couple things. And so we're going to try to give you an overview and how this all fits together and why you care. So as we get into this, let's start out. What is virtualization? Well, virtualization, as this says, is an abstraction of computer resources. Access to resources are consistent before and after the abstraction. Resource abstraction is not limited by implementation, including underlying physical implementation. That's a nice thing. What does that mean? Let's translate in English. we're going to talk about initially. Initial virtualization is creating a program that we have that when you run inside that program, it'll appear that you're running in a piece of hardware. You can't tell the difference between running inside that program and running on a bare piece of hardware. And again, why do we care? Well, most modern computers are from Intel, AMD, and other places. The processor, the memory, and the resources have gotten so powerful, they're much more powerful than what any single application usually needs. So what do? I've spent all this money on this server, and I'm only using a small piece of it. That doesn't make sense. So what happens is that we have the ability to split that resource up and have multiple people use it so we can use more of that. So we can use more of that power of that hardware. As we'll look at it here and get into it, there's some other reasons why we care about virtualization. I'm sitting here at a computer, and I've got a bunch of different servers out there in my environment. I got a bunch of servers I got to manage and everything. I have all this hardware, and somebody from development comes up, they got this new app they want to run. And so then I have to go down, ask them what kind of resources it need, go find a catalog, see what kind of machine I need to order it. Well, I can't order it, so now I got to put a rec in. Then what I have to do, I have to go get the rec approved. Then somebody might be able to order it. Then it may come in. Then I may have to get somebody to go mount it in my data center. May have to put it together, wire it up, configure it, give it an IP. Finally, I can get, after days, weeks, months, and if you're in a big corporation, it sometimes seems like years before we get the server back up, we can finally get the server running. And that's not efficient use of resources at all. We've learned. It's hard, it's painful. And what do I do in a situation where, marketing's going to run this promo, and they tell me next week you're going to get hit with a bunch of traffic. So how do I get a server in time and resources in time to scale up behind my load balancer all this traffic? Well, that's the idea of virtualization. It allows us to move nimbly, so I can take all these machines, create them in a virtual environment, and I can, because the data center has got enough resources, I can create new virtual machines on the fly very quickly and shut them down quickly so that I can scale up, I can scale down, I can bring in new applications. I can do all this without any problem. And so if we look at this, we now run, what we do is our machines, those servers on a big piece of hardware using some sort of hypervisor. We're going to talk about that in just a minute. And each of these has an operating system. To each of these little machines running on that hypervisor, what we have is each of those machines think they're running on their own little piece of hardware. And if I design the environment, it's almost virtually impossible for the application to know whether it's running on real hardware or an emulated environment. And the beauty of it all is that with lots of new technology in the core, in the kernel, lots of new technology in hardware, we can get performance almost equivalent of having our own physical piece of hardware. It's very performant and very useful, and the beauty of it is we can create and destroy these things almost immediately. So this has become the need and the desire why we have virtual machines. In this case, a virtual machine now, we'll get a little more English-like and a little more what we can understand. A virtual machine is a software construct that mimics the characteristics of a physical server. I think that makes a little more sense. So that if I create a virtual machine, it's going to, in that machine, you'll install an operating system just like I would if I had my own piece of hardware. I'll load my application into it, and when all that's running, it will appear to me as if I had a server racked up in the data center. I won't know the difference between that, whether I had a physical server or I have a virtual server. They do all the same things. The nice thing about the virtual server is I didn't have to go to the catalog, find what server matched, go fill out all the recs, go to my capital team, get that purchase approved, then get it ordered, get it brought in, go through that whole process. I don't have to do that. The cloud technologies allow me to go to a cloud interface, and I can immediately spin up a machine. For example, for this class, Monday, I'm putting together, and I have all sorts I've recently retired. If anybody that's ever retired understands that the first thing you have to do, if you're married, is you have this long list of things that your beloved, dearly cared for spouse would like to see done around the house. And I have been painting and painting and painting, and I had an unfortunate situation in the family that I've had to take care of also. So I've had lots of work to do, and I've been trying to balance that and get this presentation together. And as typical, I put everything off. So Monday, I'm going, oh, I need a lab. I knew what I wanted to run for a lab for this class. We're going to run a lab in a little bit. But Monday, I have to go do this. And so instead of, we have what, 50 people here, instead of buying 50 machines for you all to get into, I can go create a cloud account, spin up 50 machines, install the requisite software on there, and have them all available for everybody to run a lab, and you're going to be a machine that looks like I had physical hardware there. And I can do this in a matter of a couple hours. I was able to put together this lab. Now, I knew what I was doing. I've done this lab before, and so it wasn't like I just did everything from scratch, but I knew I could set this up very quickly. That is the idea of the virtual machine. It's the ability to do these things and have the flexibility that we can create servers on the fly very quickly. And it has allowed our internet to grow the way it is. So what are types of virtualization we may see out there? There's a wide range of things that have driven this that we can see. There's server virtualization, which I've been talking about so far. That we're all familiar with. We see it. We see also client desktop application virtualization. Any of us here work for a company where you get a thin client and you log in to get your desktop. You log into a virtual machine. Some folks have that. The companies have gone to that. Why? Because I can buy you for your desktop machine, your laptop, even something like as cheap as a Chromebook, and yet you can have access to the full corporate resources of a desktop by logging into your remote virtualized machine. So we have that type of virtualization. Network virtualization. I've worked with this. I've taught classes on that. But what is the thing that happened? We see projects springing up like it. If anybody's familiar with Open Daylight. The idea of this is something that's happened in the last 15, 20 years, is the idea of virtualized networks. You hear the term software-defined networks. The bottom line is the ability to, through software, define your networking environment. Break it up, make it appear like, again, real physical network, because in the cloud environment, when I'm even doing server virtualization, that whole networking environment is something, the load balancers, the routers, are something that are created in virtual space. Yet, to me, running that server, it looks like there's a physical router out there. It looks like there's a physical load balancer. I can see these things, but they look and act real to me, even though they've been created by software. So we have network virtualization, storage virtualization. I may need additional hard drives. Anybody familiar use Amazon S3, or if you use OpenStack Swift, allow us to create large disk arrays, large storage devices for us, things like Ceph. We can create storage devices we can add into our virtual machines that look like real hard drives. They're different than how the data is actually stored in the back end. But we can use that way, this idea of virtualization for storage, services, appliance, and infrastructure virtualization. All these different ways that we virtualize, yet each of these are created through pieces of software that create these spaces. So in the server virtualization world, a lot of times we need certain things, and where that came about, the first type of things that came about was way back when. I remember back in the 90s working for a company called Motorola Semiconductor, and I had Apple machines. And then as I moved into 2000, I moved over to Linux as my machines. And I had need on my Linux machines to run some of these old pieces of software that I'd had from the earlier days. Well, in that case, what I was able to do is install a full emulator under my Linux box. In this case, I used one called Box that would create an environment that looked like it was an Intel processor into which I could install Windows and my application and run it. Full emulators, was it slow? Yeah. But it did what I needed to do, and fortunately the software is not very complex. Emulators create a full virtualized environment that emulates in software everything that a processor does. So it looks like a raw processor, but it's doing that in software. QEMU is another emulator that came out in Linux later on. Again, a full emulation environment. The problem in full emulation is that it gets slow. And it doesn't necessarily allow me for running multiple machines in the same environment. So we came up with the idea of the segmented use of host processor. One of the things I didn't mention, I talked about IBM starting doing virtualization back in the 70s. Back into the 90s, a company came up called VMware. And they decided they could do something better, and they created one of the first what we call hypervisors. And is these hypervisors that they provide. A hypervisor is a piece of software, again, that acts like this emulation layer between the application and the host hardware, but it is much faster and can take use of software hooks and can take use of other things to avoid having sometimes to do full virtualization, but can do this virtualization not by doing it as an emulated environment like box. It is emulating each machine instruction. It's actually running on the host processor, using the host processor architecture, and just emulating now the rest of the hardware interface. And so we get into something that we have called type 1 and type 2 hypervisors. And this over time is kind of blurred. The original hypervisor, Zen, was one of the earlier ones. I won't say it's the original one, but one of the very early one, didn't have an operating system. It was the operating system and could provide environments for multiple machines running on it. It would act as this interface between the actual processor the program is running and the hardware that you thought you would have for your operating system. We then came up, and then things, type 2 or hosted hypervisors we've seen. Any of y'all ever used something called VirtualBox? I think we all have used it from time to time. It allows us on our machine, whether you're running Windows, whether you're running Mac, whether you're running Linux, you can run an environment that's just like for a machine. But it's running using the host operating system. Type 2 require a host operating system, or type 1 run on the bare metal. There's a big difference. We also have something in Linux we use called KVM. KVM is an outgrowth of the emulator QEMU, but KVM uses kernel modules to become a quasi type 1. Type 2 is called either one, type 1 or type 2, but it uses the pieces in the kernel to become a hypervisor. And as of about 6 or 7 years ago, KVM grew up to be a full-blown professional level that can do everything you want in the cloud world and has become generally the hypervisor of choice in the Linux world that people use. So we now have the type 1 hypervisor. You have your bare metal. The type 1 hypervisor runs directly on the bare metal, and the various operating systems or virtual machines run on top of that hypervisor. The hypervisor can handle that. And if you want to visually see the difference between a type 2, we have our bare metal, the operating system installed, and on top of that runs a type 2 hypervisor that can support multiple virtual machines depending on the resources available in that environment. So that becomes the difference there. One of the things that we get into in trying to run that is we'll find a term you may run into in virtualization called paravirtualization. Because the problem gets into is if I have to, through software, fully emulate, I gotta be careful, I want to wander over there and then I get in front of the speaker and then the speaker picks up on my mic and it sounds funny, so I'll try not to do that anymore. If I have to, through a hypervisor, fully emulate something like a NIC card, that can be a bit slow because this NIC card, whether we realize it or not, has its own effective processor that does a lot of things to offload a lot of these network functions and offload part of the network stack onto that NIC card and do those things. So now if I'm having to emulate that whole card in software, that may be, as in my hypervisor, that can be a little slow. So what I need to do, and what we came up with the idea is what we call paravirtualization. And oh, by the way, if you have a question through this, please raise your hand, because I entertain questions. Behan has a mic. We want to make sure it gets recorded. But please raise your hand, because as I'll say when I teach a class, the only dumb question is a question that didn't get asked because you went away not understanding something. So please ask questions, you have it. What it does, it provides special APIs to virtual machines to optimize their performance. In other words, there may be places that, if I'm using a disk controller, I may give you an interface that you hook to, but I'm going to use the underlying hardware instead of having to emulate that in my virtual machine, in my hypervisor. That makes, since I'm using the hardware functions like the NIC card or the disk controller to actually perform the activity, that makes things run faster. So a hypervisor can give much more performance if it's doing what we call paravirtualization. It's, again, similar yet not identical to the underlying hardware-software interface. It may use some of that hardware to accelerate things, but it's not providing all this. You can't directly get to that hardware. It's providing a standard API to get to it where it can take advantage of it. And its support is part of the kernel. And it requires specialized drivers. And again, we found this type of KVM uses that. So we've had that type of virtualization, paravirtualization, in KVM since 2008. And it's been about 2008, 2009, 2010 where KVM had the hooks and finally had the performance it took to become a full professional grade, if you please, hypervisor. Cloud computing then, we've heard this term and we've seen it. We've probably touched things like OpenStack, you've heard AWS, and there's been a whole bunch of other cloud, cloud almost as a service type thing out there, all sorts of different folks. Cloud computing basically provides a software interface to the hypervisor. So if I go to Rackspace and use its OpenStack interface, if I go to Amazon and use its interface to its cloud, I get a web type interface. All that's doing is once I've shown these folks I can pay for what the resources I'm going to do, then it goes through software. The back end talks to these hypervisors and causes those to be, finds resources in the environment, and it creates a virtual machine for me. It may have to then also construct the networking interfaces because I have to have outside IPs. I may need routers, load balancers, various things to hook those things into, but it creates this through my construct. So I get a nice, easy use interface, or I may have an API that my own application can interface to cause these things to be created, to hook up. I don't have to understand, like when I've taught OpenStack classes, I've made the comment, I could be Mr. OpenStack. Because anything OpenStack does, and same thing through Amazon or any of these others, anything those do, all these APIs do is cause code to be run on various Linux boxes that are actually running the implementation. So I could be Mr. OpenStack, like I say, somebody passed me a note and says, I need a virtual machine, and they tell me what size and everything. I then can go on my machines and create that virtual machine through the command line and create all the networking stuff. And when I'm done, about 3 weeks later, because it takes me that long to get all the typos out of my stuff and actually make it work, I can go tell him, here's how you access your machine. OpenStack does it in seconds. AWS does it in seconds. And that's the difference. That's what this cloud computing does. It provides a software interface to hypervisor, and so that we can remotely create all these constructs very quickly and very easily. It usually includes several, I can't type there. Hey, I'm an engineer, and why do you think engineers created spelling checkers, because we can't spell? No. I missed that one. Several types of virtualization. For example, for a basic Amazon OpenStack type environment, you at least need a storage network and machine that you have to bring up. You may have other constructs you may need and want. They may provide those. But that becomes typically from a cloud computing environment the bare minimal you'll need. And like I mentioned, Amazon, Openstack, various things you may run into depending on the environment. If you're doing public cloud, you're most likely running into Amazon, although Rackspace and a few other places do have OpenStack versions. If you're doing private cloud, then it's probably OpenStack because that's the type of environment. I have to watch the time, so I make sure I leave us time to do the lab at the end. Lab won't wait long, but it should be a little fun. So we've heard this term called containers, because that's the next progression. We had all the virtual machines, and all of a sudden we heard some term called containers. So what is a container? Why do we care about it? How did they come about? At the time that all this virtualization, there were some concepts being built into the Linux kernel. And this came from, like I mentioned, it actually goes further back. Elle up here, I'll embarrass her. She used to work on my team in OpenStack, and I stole this particular slide from her that she did in the past because we were working on something here. But it gives an idea of the history of containers. Because just like virtual machines, like I mentioned way back here in the 70s, IBM doing virtual machines, there's some things we've done to create containers. Containers really are not a direct, but an indirect offshoot of something. Anybody ever run chroot jails on your Linux boxes? So you create this directory and create as a chroot directory, but to get anything to write, you had to copy all the libraries and everything that the process that would run in this jail would need. It was still taking advantage of the kernel that's running the machine, but it would help you run an isolated environment. For example, running an FTP server was typical in a chroot jail, so you wouldn't have to worry so much about somebody breaking into your machine and taking over your whole machine. It could run in a secure environment. Well, an offshoot of that, again, I said chroot, and we have jails. We came up with the idea of process containers, but to really do containers the way we do it today, we needed something called namespaces. How many folks are familiar with Linux namespaces? And it's important. This construct is a critical concept to get across for containers, because we find in the late 2005, 2010, maybe 2003 to 2010 environment, we find namespaces being brought into the Linux kernel. The first one was a network namespace. And in doing virtualized network, even without containers, we take heavy use of network namespace. If I create a network namespace, it's an area, an isolated area for networking. It has its own network stack inside it. The kernel can't see it. The base machine can't see that namespace. You have to be inside the namespace to see what's going on. I can create virtualized Ethernet card interfaces inside that namespace, give them IP addresses, routing table instructions. All the things I can do networking-wise, I can do inside that namespace, but it's isolated to inside that namespace. So I'll have to create a virtual Ethernet pair, one inside the namespace and one outside, to actually connect into my namespace. What that does is create a convenient construct so that if I need a NIC card with the same IP address range of my machines, or the same IP address that maybe want to interface because of the way somebody machine, I can do that, and the machine won't get confused. If I create two NIC cards with the same IP address, what does your Linux kernel say? It'll slap your hand and say, you shouldn't ought to do that. And you can cause all sorts, if you ever figure out how to work around some of the network constructs to stop that, you can cause yourself all sorts of networking chaos and problems by having done that. And so namespaces allow me to isolate those things so that, for example, in a virtual environment, when you create a virtual environment in your machine, you may want to have a specific IP address for its private subnet. By doing that inside a namespace, you don't have to worry about it conflicting with anything I put on that bare metal machine, because it's isolated. And so namespaces allowed us to do that. But there's a number of different namespaces besides networks that we had to create. In this case, if you look at it, there are a number of global namespaces that we need. You potentially need all of these. You may not need all of these to create a container, but you could, in some cases, need all those. For the mount namespace, this is, if you please, disk namespaces, file system namespace. It's an isolated namespace where we mount things. So it has directories that are isolated inside that namespace. In other words, my base machine cannot see inside that namespace, and that namespace cannot see on my machine. They're both two isolated environments, totally separate. So to create a container being something that's going to run a program, I'm going to need files. So I'm going to create a file system namespace. And in that one, I'll probably have a proc directory, /proc directory. Remember, in the Linux kernel, /proc has information about our system. So we'll have things like that we can create for our CD-ROMs or other resources we may want to share. I'll talk about network namespace. I already mentioned that, isolated. We may need a PID name. We're going to need a PID namespace because we don't want, if we're going to create an isolated environment, and we're going to create a container, we don't want the PIDs of our container trampling all over the PIDs of our base machine. That would cause wonderful confusion. So we need an isolated environment for that. Time, UTS, so our time system. IPC, everybody know what IPC stands for? Inter-process communication. It allows different processes to communicate. But if we don't isolate those, then we could have things tripping over each other. So we create that. And user namespace for our usernames. We can create one or all of these. For example, we don't want root inside a container to have root access into our base system, do we? That would be bad. Somebody inside our container can start changing our base system as root. No, we want to create a namespace for our container. So root in that also goes to a unprivileged user in our main machine. So that root user can't do anything in the main machine, but it has full access inside our container. So we need multiple of these namespaces that are set up in different ways. And this is what our container software has been able to take advantage of. So if we compare the difference and why we care and what containers bring to us, is that a type 1 hypervisor, we have our hardware, our hypervisor, virtual machines that has its own operating system, its own /bin, libs, and then applications running in those. If I do a type 2, hardware, operating system, hypervisor, and then everything, all this operating system things installed several times. If I look at the container has the hardware, the operating system, and then it will mount inside the container various bits and pieces off the bins and libraries of the machine, or we can install it. So I can use a container that on the base machine is running Ubuntu, a Fedora container, for example, and run that. It just means I have to put more stuff inside my container. Or I can run a Ubuntu application or Debian application, a container running that, with just a small amount of that. So it just depends on how much I have to sit. So effectively, inside that container, I'm only putting the pieces that I need for that application to run. I build that container that way. We have also created, over time, because of that, because of namespaces, who wants to go build all that by themselves? It takes forever. I don't want to do that. So we've come up with, there's tool sets that have evolved over time to allow us to build those. LXC, and there's a bunch of others. Probably the most popular one we hear about nowadays is called Docker. Docker being a tool set that allows us to build and manage containers. That's what it does. And we found that that's become very popular. There are others around there. There are newer ones coming up from time to time. We may or may not use those. But again, containers are just, it's still virtualization. Each container has its own network interface and IP address inside the network namespace. And they can be bridge routed just like your own favorite VM. It has its own file system. The Debian host can run Fedora containers, like I mentioned, and vice versa. It has its own isolation. These namespaces are built up, give us isolation. When I mount a file system in there, I can mount it as give it read-write to the base root file system or just read access only. So I can control what accesses a container would have to the underlying file system. And all the files, all the securities of users and things, again, apply. So we have all the different securities we can do. So we have security here. Container A and B can't harm or even see each other. I only know, if I'm in a container, I only know about myself on that machine. Likewise, if you're in your own container, you can't see my stuff, I can't see your stuff, I don't even know you're there. And that's the way it should be. Also, resource usage. We can set soft and hard quotas. Anybody ever do anything with something called C groups? If you haven't, you should go read and study C groups. C groups allow you to isolate and tweak parameters as a usage on almost everything inside that kernel. And you can create a C group for each virtualized machine and a C group for each container. In particular, Docker and those typically do that. So I can control some of the problems that we can occur. If you've ever done virtualized machines back when, you don't see this so much anymore because of C groups and other things. There's something we call the noisy neighbor problem. Having come from Rackspace early on in the virtualized machine environment, what we'd see is people would come up and spin up maybe 20 virtualized machines in the morning, and you'd see them run performance tests on them for a little bit, and they'd shut down about 2/3 of them. Because what they were doing is they were trying to get a virtual machine with X resources and be on a particular piece of metal that wasn't being used very much. So they could then take all the resources over and have high performance. Because if you were on if you're a virtual machine where another virtual machine was heavily using the disk I/O, that other machine could use up all the disk I/O and affect your performance. And that was a problem early on. C groups are a fact in the Linux kernel, allow me to prevent that. I can give a virtual machine only up to a certain percentage of the available disk I/O. That way, there'll be plenty of disk I/O left for other virtual machines. And so that isolation and the quotas for RAM, CPU prevent virtual machines from having other adverse effects in that environment that we can create. Okay, now you've heard all the latest hotness. Everybody's heard, who hasn't heard about Kubernetes? I should get no hands. Everybody's heard about Kubernetes, right? This is the latest hotness we have of things going on. Well, Kubernetes is an interesting technology that Google brought to the market, to the container market. What they found is that in a lot of large applications, there's a better way of doing things. Now, Kubernetes does not, I see the advantage of Kubernetes. It's a great tool in certain environments. It's not this cure-all for everybody that it's being sold as, but you need to understand what it can do for you, and it can do some wonderful things if you have the right environment. It uses containerized infrastructure. In other words, Kubernetes will sit on top of a container controller, like Docker or any of a number of them. Principally, people today are using Docker, although there's some interest in looking at using other type of container tools, but Docker is the principal one. Again, it comes from an idea of application-centric management. We're going to take an application, we're going to break an application down into what we call microservices, little tiny pieces. Each of these can stand alone and are independent of each other. They need to talk to each other. And if I need more performance in a particular area, I can create more of these microservices in one area, which will help up that particular part of the application. As such, it becomes an auto-scalable infrastructure. It's an infrastructure that can scale up and scale down. We get environment consistency across development, testing, and production. It's a loosely coupled infrastructure, and that's why I'm talking about microservice, where each component can act as a separate unit. So things can be broken down into very small pieces. Because of the way these work and because of the containers and the way they involve, we get a much higher density of resource utilization in our machine and a very predictable infrastructure that we have in this. So what is Kubernetes? It consists of a Kubernetes master that has a number of different pieces. There's what we call an etcd or etcd server. There's a base database server that contains information about your environment. Now, etcd servers are designed to be replicated database servers. So I can run one of those and they will stand up and they have resilience. The only one that sees that, though, and it keeps information about what's in my environment is the Kubernetes master. It provides an API server. This is an API into which I make requests to my Kubernetes. I want to do things, find information out about it. It has a scheduler, which then decides where containers and things we call pods are built on the various worker nodes, and a controller manager. And there's some other little pieces we can talk about. And then it will have what we call Kubernetes nodes. These are the ones that actually where things are created and are going on. On those may have Docker running each of those because that's where our containers are going to be built. It'll have something called kubelet, which then can talk back to the controller manager, and the Kubernetes proxy, which does certain activities. And it's on these nodes into where we create our containers are actually the bits and pieces of microservers, the pods for our application. Or if we look at that in a slightly different environment, you can see the Kubernetes master, the API server, exposed API, etcd server, the controller manager scheduler, and the various nodes that give the various services out there. Okay, and again, a third way of looking at it, the master node. It's the master node in which we all interact because it provides the Kubernetes API that we say, hey, Kubernetes, go do this for me. And then the Kubernetes will go build something. Now, it may build pods and containers in a pod. It may build some services or accesses, how we can externally and do networking pieces, how we access our environment. And there's lots of different things it can do, and this class is not designed to be a class of how Kubernetes works. That comes later. If you stay through all the classes we teach, we'll have a little more about Kubernetes later on. So, we've heard that. Let's keep a couple more pieces of the whole cloud environment, and then we're going to try to do a lab. Let me make sure I'm staying on track time-wise here. Last I looked, I was all right. Okay, we're all right. XaaS, everything as a service. We've heard this, and basically what that came out was, again, with that first group of virtualization, we found people starting to offer various things. Software as a service, platform as a service, infrastructure as a service. You can think of things like Amazon Cloud Service or OpenStack of being infrastructure as a service. I can't get it out today. Reset my mouth here. Infrastructure as a service. Basically processing, storage, other computing resources, probably some networking as a service, so I can go create a small environment for my applications. I can add servers, I can add routers, load balances. Platform as a service deploys the various acquired applications on the cloud infrastructure. In other words, its ability to create an application. For some folks, I set up a small WordPress site. And I need the one I'm doing, somebody's had one set up there, managed it, and I can help them manage to do it. I need to now, they want to make some changes, so start using more disk space, and I don't feel comfortable taking advantage of the particular person, so I need to find another WordPress site. WordPress sites are effectively application as a service. I can go out and buy that. I need to create a MySQL server. If somebody has an application as a service, they will spin up MySQL servers for me, and I can then put my database or various other database servers. So application as a service there allows us to do that, becomes a platform as a service, so we can deploy those in there. Software as a service, again, different type of ability to run various software applications in there. What this came out is people then said, hey, I can almost give anything as a service and sell that. In fact, if I look at my customers, typically the customer doesn't want to buy my Quicken books. They just want to be able to use that. And I could provide Quicken as a service, for example, and sell that. And people don't have to worry about buying a machine, installing it and everything. They just create their database and start running with it. And so what we found, what we call something called product service systems, is a cohesive delivery of products and services. So I can buy that as opposed to having to buy maybe Amazon, a server, and install that software on that server and go do that. I can just get that in thing. For example, WordPress is a service. I don't have to install it. I don't manage it. There are ways that you can get vulnerabilities in that you have to keep up to date with, all that work that you have to do. I don't want to know about that. I just want to be able to create my blog site. And so I can buy those things that way. And that's where we come, and the term then servicizing has come about because of that. Basically, it says, I am going to create a company that can offer this service for somebody, and I'll sell that, and people use that chunks of that service instead of having to manage the whole underlying infrastructure themselves. So that's what that becomes, and all this as a service stuff. And so we see today software as a service, infrastructure as a service. They're just different. That first word is just a different word to describe a bunch of features we have we're going to offer. Bare metal as a service. You can go to Rackspace, and I'm assuming I haven't tried it with Amazon, and you can do that. I can buy a whole piece of bare metal server and spin that up through that cloud interface. Bare metal as a service. And storage as a service, desktop service, even disaster recovery as a service. So all these things, there's a wide, again, that's why we have the asterisk or X as a service. Whatever, it's up to your imagination. If you have a product that somebody wants to buy, you may want to offer that as a service, so they don't. It makes their life easier. Guess what? You get to charge more for that too, then, because you're providing more functionality there. So these things, and so we see all this as a service stuff occurring today because of that. Okay. You probably have heard this term, and if you haven't, you're about to hear it, the term called OPNFV. And this has come about because of something else that's happened in the cloud world. That the cloud world has, and there's huge interest. If you are Verizon as a provider, I'll pick on Verizon today, but there's AT&T and anybody else. You provide network broadband to all over the world. Because Verizon not only we're familiar with them as a cell phone, but they do lots of things. And if you as a cell phone want to watch YouTube, there's lots of things they have to do in their infrastructure to try to make that happen and convenient to you. There's a lot of different network pieces. And in fact, hooking the cell phones, hooking different mobile services, hooking modems up, there's lots of different things they need to provide in their infrastructure to make that all at work. That has created a huge quagmire of products that they have to implement out there in their environment to make that all work. It makes Cisco very happy. It makes Brocade very happy. Because people, every time somebody comes up with a new thing, Brocade, any of these network providers, Cisco, what they do is they create a new box that implements that. And they charge bucks, and then large bucks, and the infrastructure people have to pay that. They don't like that. Because then when that protocol tweaks, they probably can't reuse their old box and add new software. They probably have to buy a whole new box. And they're spending large amounts of money. So they want us to use something called network function virtualization. If I get into this next slide here, we're going to have something called network function virtualization. In other words, all these network functions I used to buy a piece of hardware for, and I spent big bucks because these hardware were very well designed. If I buy, for example, need to get into an environment and log into it, the network access, load balancers and things like that have hardware that's designed to be very high performant. In other words, they can handle large amounts of network bandwidth. And they have specially designed hardware. The Verizons of the world buy those because they have to, but they don't like them because then if it changes, the costs involved and they don't last that long, they may not be able to get all the value back out that they had to pay for it before they got to buy a new one. The advantage of network function virtualization, if I can do this in software, then I get the advantage of, hey, if the protocol changes a little bit, it's just a different virtual machine. I don't have to buy new hardware. The problem you get is that you need very scalable, parallelized function virtualization because you can't do things in software as fast as you can do in this finely tuned hardware. And so that is a lot of money is being spent and a lot of work is being done to create this idea called network function virtualization. And all these big broadband providers are well down the path of moving that way. It's going to cut a sizable piece of money out of the people like Cisco and some of the Brocade and other folks, Big Switch, but it allows them to be more responsive to you and I. And they do all this how? Through cloud-like environments. So network function virtualization is out there, and that's going down, and a lot of those folks are using that heavily. The other thing is this is open platform. Now, OpenNFV would have been a much nicer name to use for this project, but HP went out and trademarked the name. Even though their product's really not open, but they trademarked the name so Linux Foundation couldn't use it. So it's something's called Open Platform, OPNFV, that is created. Basically, it's a group out there, sponsored, that plugs into Linux Foundation. You can go to OPNFV and find it. It's collaborative open source platform for network functions virtualization. There's software being defined there and some hardware being defined there. You can buy these things, and it started by the Linux Foundation in 2014 as a response to all the needs that go on in the network virtualization environment. In fact, one of the things you find is the Openstack has lost its hotness, and everybody, it's not really. Openstack is being used very heavily by these people. If you go to these folks, they're using it all over the place because this is their private cloud environment to cloudify their whole network environment, because they can be much faster and more efficient and much more cost-effective in providing services by doing it that way. So, and that's why I talk about Kubernetes. Kubernetes is a hotness that nobody knows how to use right now. Some of these other technologies that now, as they get integrated in and become very commonplace, we don't hear so much out about them anymore. OPNFV is, again, one of these projects out here that the Linux Foundation is sponsoring to help us automate network functions and software. So we can do things like load balancers, firewall, customer premise equipment, and all the other things we can go, and this is just a small list of all the different functions they're doing in software. Again, you lower the total cost of ownership by virtualizing the various functions and avoids restrictions that hardware implementations create. In other words, if I need to expand my network, I can't until Cisco sends me a new box. I'm stuck until it gets in. If it's back ordered, I'm hurting, especially if my subscriber base has grown. However, in this case, if I do it with NFV, I just need some more cloud servers to do it. So it's much easier to grow the environment. So the objectives of OPNFV is to create an integrated and verified open source platform that can investigate and showcase foundational NFV technology. At the end, most of the folks are writing their own NFV solutions. Some of that's getting moved back into it, but they have their own things they're doing also. But OpenNFV takes the more common of those and provides a hardware also environment that people can use so they can validate various technologies. And it's an environment so that also OPNFV can bless and stamp certain products so that if you want to use these OPNFV products in your environment, you can use those. So it gives it's a foundation that it's an organization underneath the Linux Foundation to help develop this and help this technology develop and advance. And it's proved very influential so far, and it's helping this whole environment grow. And in particular, I talk about OPNFV, and if you're not familiar with it, it's beyond the scope of what we're talking about today. Something called Open Daylight is another way of, through software, automating. Open Daylight is more through software, automating your whole network environment so you can manage it through tools. And OPNFV then helps certain people implement certain functions in there through virtualization. Cloud Foundry being another project that has been brought up under the Linux Foundation. It is effectively platform as a service. I mentioned that the cloud providers, OpenStack and Amazon, are infrastructure as a service. This is platform as a service, and it can actually run on either Amazon or OpenStack. It's governed by the Cloud Foundry Foundation, sponsored by the Linux Foundation. It was developed by VMware. It was software that VMware developed back around 2008, 2009, 2010 that they started going out with, that they then have donated to the Cloud Foundry Foundation, and all the code is licensed under the Apache license there. So again, what does it provide us? Platform as a service usually delivers a computing platform, including operating system, programming language, execution environment. For example, database, web servers. It's a programming language execution environment, if you please. So if you have this, you develop your application, And then you can use these tools to deploy your application based on the tool sets that are provided here. So we can deploy cloud applications. Applications are created using various provider tools such as programming languages, libraries, and other things. Basically, you as a user are going to go deploy your application. You're not worried about how to implement the underlying cloud infrastructure. So when you use Cloud Foundry and I want to deploy my application, Cloud Foundry will make all the decisions about the network environment, the number of virtual machines, all that for you. You say, hey, I want this application run, and Cloud Foundry will make it run, and I don't have to worry about all the other infrastructure involved. So users have control over the deployed application. They cannot manage or control the underlying cloud infrastructure because you should not care about that. There are 4 different, what we call project management committees that have various other implementations and pieces of software that run in there. There's the application runtime project management committee. So they have various projects here. So you have the strategy, development, quality control of the core components. The BOSH that does release engineering, deployment, lifecycle management, monitoring and distributed systems. Extensions, so extension of the Cloud Foundry run time, and the Open Service Broker, PMC. So these handle the Cloud Foundry. And so that basically, we are now roughly an hour into the presentation, which is just about what I said. And so what I would like to do is take the next half hour to, we're going to run, we'll see if we have any questions first, and then we're going to bring up a small project here. What we're going to do is I have a bunch of virtual machines. Hopefully I have enough for the audience, but should be pretty close. And I've got machines set up in Amazon. You're going to SSH into them. I'll give you credentials to get to them. And then what we're going to do, they have Kubernetes installed. So I'm going to show you how to bring up a very simple Kubernetes. In fact, we're going to bring up a web server, an image, and we'll verify that it runs. And I mean, that's just to give a touch of Kubernetes. So you'll get to see how to do some of this. But before we do that, any questions so far? Haven't seen any hands yet, so either I've done a good job or everybody is, the good part is I haven't seen any eyes glaze over and you get this forehead that has a bunch of keycap imprints and it fell and hit the keyboard. So that's good. Okay, let me get these, and I'll bring up. I have some machines too, so if I can get some help to hand out my tiny little pieces of paper. There's about 40 of them there, so we might be 1 or 2 short. But if you don't get one, just look over the shoulder here, and it'll work here. Everybody ready? Okay, so the first thing we have to do for Kubernetes is kind of like, has anybody ever used Amazon Cloud Foundation or OpenStack Heat? Those are also 2 software ways of defining your environments. Well, Kubernetes needs a definition of an environment, and it's what we'll call, it's a file that we create that Kubernetes will use to create its environment. So we're going to need to create that first file. So let me show you what you need here. And what you'll need to use your favorite command line editor. I know everybody uses VI as opposed to Nano, right? But if you want to use Nano, you can. Basically, we need a file that looks just like that. But notice right here, this is 2 spaces, 2 spaces, and 2 spaces in front of there, and 4 and 4. Spaces not, let me see if I can walk and not trip over. Those need to be spaces, not tabs. Now, I ended up, I could fix that. But I ended up using a proportional-based font, and so you don't see the spaces right. I need to use I should have changed that into a courier type font so it would have shown better. So basically, it says API version colon space v1 kind colon space pod meta colon 2 spaces name colon nginx spec colon 2 spaces containers colon 2 spaces dash space image colon space nginx 4 spaces image pull policy always, and 4 spaces name nginx. So let's go ahead and create that.
So they're looking at the slides, they might be able to cut and paste it.
Yes, if you pull the slides up, you should be able to cut and paste. You see, what I'm going to do is cheat here. I'm going to go here to this slide right here. This slide right here. We're going to do it, and I'm going to cheat. I'm going to cheat here because what I'm going to do is when you cut and paste from PDF is always problematic, as Jerry is telling you, because PDFs don't always treat you nicely. I'm going to try this. Let's see what happens. So now I'm going to come back over here. I'll bring my SSH session, and we're going to call the file nginx.yaml. So I'm going to do a vi of nginx.yaml. And I'm going to do an insert, and I'm going to paste there, and it didn't get it right. So let me show you the things I got to change here. Metadata, there should be 2 spaces there. Containers should be 2 spaces there. Image should be 2 spaces. Image pull policy, that image should line up with that image. That name should end up with. Now, use spaces, do not use tabs. Use spaces, do not use tabs. If you use tabs, when we get to the next step, you will fail. I guarantee it, you will fail. So we need that. I see something that might be some extra spaces here also that I need to check. Mine's doing funny things here. Okay, it looked like there was a space there, and I don't think there is. No, there's not. Okay, make sure there's no spaces there between the ends thing. It's just the way my session is doing right now. So I'm going to do a right quit, and then I'm going to come back into my slide here. And we'll go to the next slide, slide 5. It's going to tell us, so we're going to launch this. We're going to create this container. kubectl is the base command that we use in Kubernetes to do things. It actually, there's other things going on behind the scenes I'm not going to talk about right now, but it makes a request to the API server. What this is going to do is tell the API server to create a device based on that file that I just made. So what I'm going to do, if I did this right, we're going to see if I did this right. And who knows, we'll find out real quick. So I'm going to do a kubectl create -f, and I'm going to do nginx.yaml, and we'll see what happens. It will tell me whether I did, oh, it says it did it right. It says it did something. Now, I don't fully know whether it's working or not, but we're going to find out. Okay, so if you create that file the way I said, well, I had it up there. If you downloaded it and create the file successfully, then we can check. So let's ask kubectl, did things get running? We're going to do get pod. Let's see what it is. Oh, it tells me that I have a pod called nginx and that it's running. Been running for 29 seconds. Well, that's a good sign. It says we did something successful. So I hope anybody got to this point here? Okay. Good number of folks have gotten here. Anybody struggling? No, you don't have to admit. What you'll find is that this is typos in that previous file are critical to not have typos. You got to get it right. The syntax, hey, it's like any computer language. Syntax has to be right for it to work. Why do you think I'm not a programmer? Or let me put it this way. Most folks, when I write code, say, don't do that. It's probably why I never became a programmer, because can I write code? Yeah. Is it ugly? Yeah. I recognize that. Usually when I write code, as long as it works, I'm not trying to maintain it. As long as it gets something done, I'm happy. So I have something working here. Let's find a little bit more about our pod. kubectl describe. Let's say describe pod, and engine gives the pod name. That's this name right here. It says, so let's describe that pod. And notice what I get. I get a whole raft of information about that pod that's going on. And I can go over here to my scroll bar. We can look back up. It's telling me that the events that happened, that created the container there, successfully pulled the image. Basically in this, if you notice, I gave an image name. That image name, in this case, Kubernetes has a public repository of images. So it pulled an image out of that. An image is the set of files that I need inside my container to make this base container work. And the other description in that file told Kubernetes how to tell Docker to build my container and put an image in there. Now, when you build a container, the container does not start with an init process. It just starts with a particular process. In this case, the only thing running in that container is that Nginx process. If I go inside the container and look at it, I don't see an init number one process. The init one process I would see would be just Nginx. So it doesn't work like a normal machine. This, again, we're lightweight. We don't need all that other stuff. We can use the init process from the underlying kernel. We don't need that inside our container. So we have that. So I have things working. It tells me things about the volumes if I mounted external volumes inside that. It tells me all sorts of information about the environment that I have that I can go look through. Now, what I'll care, if I'm running a web server, now Kubernetes does not publicly expose this web server. And we're not going to go through the steps it would take to publicly expose it. We could do that. We create a service and do that. Come to our Kubernetes class later on, or take our full class. I just sat through one last week. Take our full class, and you'll learn how to do all this. But this is just a real quick. But let's go through. There is an internal IP address that server is running on. So let's pipe that to grep, and grep for the words IP. Let's see if we can get an IP out of that. And sure enough, I get a 192 IP. So let me go ahead. Where'd my mouse go? Help. With two screens. There it is. I should have brought up my regular mouse. The problem is, one of the problems you get into touchpad PCs, first off, you have two screens, you got to figure out what your mouse is, and depending on Linux, it's going to change between an arrow and a cursor bar, depending on which window it's in. So that also is a distraction. And then your tab, one side of the tab is to scroll up and down. The other half of the touchpad, one half of the touchpad moves the mouse, the other half does scroll. So if you're getting the wrong side of it, then things don't work. So it can be a real pain sometimes. I'm just whining and complaining, I know. Okay. Let me grab that IP, highlight my IP there. Okay, let me copy it. And then on my command line, let's do a curl, the http:// that IP. So if I have a web server running, I curl from that IP, I should see a page, right? Then we'll know whether that works. And sure enough, I see the default Nginx web page from curl. So basically what we did here was very quickly built a Kubernetes image, and we built a Kubernetes container pod. We built off a predefined image that's out there in the Kubernetes repo. And by doing that, it started up, and we have a Kubernetes web service. We'll look at a couple more things on that, but it gives you an idea. Kubernetes, in its simplest state, is not hard to do. In fact, if we put an application build microservices, we can take a running container that we have and save that as an image. And we can save that either in a public repository or a private repository. It could be out into the public or private repositories on the web or ones in our environment. And we can then further, if we want to automate the process, have Kubernetes spin up these automatically. We can create things like deployments in Kubernetes. Deployments then uses the scheduler and other things to monitor our environment, so we can say how many machines I want, and we can create them behind a load balancer. And we can tell it under the conditions in which it should scale up other machines, so that if we get heavy load on our environment, it can spin up more machines or shut them down. And if machines fail, it will start new machines up. And the wonderful thing about deployments that we have also, it allows us to do version updates. So I can roll out a new update on my application automatically, and Kubernetes will manage that for me. It's a great little tool, and it's become very popular because all the features that Google rolled around, the basic container environment that allows me to do lots of very complex things, and Kubernetes can manage those things. I'm only touching the hem of the garment, as you can see there, but it can do things, and you can see right there that we have a machine running there. I can even also take the output of that, use from a Kubernetes, and create a new text environment from which I can build new machines and I can send to other people. Any questions? Hopefully that got you. Now you can go back and tell your boss, I learned how to spin up a Kubernetes container. I've done it. So we've done it. I appreciate for your time in here. I think we're done on time, maybe a few minutes early today.
Yeah.
We're supposed to go to 12:30. We're at 12:23, so we're 7 minutes early, so we're right about where we want. Again, any questions? If not, thank you.